Hi, welcome back. Lecture number 2. This one's about absolute value. And if you thought you knew absolute value, well, think again. This basic idea, we're going to talk about the geometric interpretation of absolute value as well as one for an algebraic version. And then we're going to culminate this lesson into a proof of the triangle theorem, the triangle inequality theorem. So let's get started here. We're going to get going with a geometric version. This is probably the one that, if you know about absolute value, this is the one you've probably heard about the most. It is these vertical lines mean the absolute value of something is the distance from x to the origin. And the origin would be 0. And we're talking really just about a simple number line. So the origin is 0 on the number line. So for instance, the numbers 5 and -5, they both are 5 units from 0 or the origin. And so the absolute value of 5 is 5 and the absolute value of -5 is 5. So here's a few more examples. The absolute value of 17 is 17. The absolute value of -2/3 is just 2/3, and the absolute value of 0 is 0. It's really just distances. And the idea that no matter what, the distance always comes out to be a positive value, because you can't have a negative distance. How do you go -2 feet? And when we evaluate these expressions, we can treat these absolute value symbols as parentheses. So in the order of operations, we would have to do the parentheses first, and so we would usually do these absolute value symbols first. So 6 minus 7, that's -1, and we keep this 5 minus here, and then the absolute value of -1 is just 1. So then the 5 and the minus stayed, and 5 minus 1 is 4. And then here we have absolute value inside of absolute value. So there's this large absolute value outside and the smaller ones on the inside. So the absolute value of -2 is 2, minus right there, and the absolute value of -3 is 3. And then you do 2 minus 3, which is -1, but we have the larger absolute value, which the absolute value of -1 is 1. Not super tough. And as we were saying in the beginning, we have the geometric that we did up here, but we also have an algebraic way to define absolute value. So the absolute value of x is itself when x is greater than or equal to 0, and the absolute value of x when x is negative, when x, yeah, then the absolute value of x is the opposite of x. That says negative, but we can also call this the opposite of x when x is originally less than 0. And so symbolically, that follows here. So the absolute value of x is x when x is greater than or equal to 0, and it's the opposite of x when x is less than 0. So here's an example of when, so this right here, -7 is when x is negative, I'm sorry, when x is smaller than 0 right here. So this is equal to the opposite of x, and the opposite of -7 is just 7. Okay, so this is playing right into here. And so by looking at the examples, which with specific numbers, you should be able to convince yourself that both definitions give you the same result. So, you use the geometric or the algebraic versions, it won't matter. So we're going to rewrite each of these in a form that does not contain absolute values. And the solutions are below. We can see here that our solutions are here, but I'm going to try to use this space to walk through this. We have, so the absolute value of pi minus 4. So what do we got there? We have something that's going to be negative, because pi, if you remember, is about 3.14. So that means that we're going to end up taking the absolute value of a negative number, something that's smaller than 0. And since it's going to be smaller than 0, we can take advantage of this. So when this is negative, meaning when it's less than 0, the answer to it is going to be the opposite of whatever x is. In this case, x is this pi minus 4. So the answer to this one part here is going to be the opposite of pi minus 4. And then we have the plus 1. Now, let me just slow this down for a little bit. If I have, as in our example earlier, if I have like the absolute value of -3, well, this is our x right now, and x is less than 0. That means that the answer to this is the opposite of x. That's what this says right here. It's going to be the opposite of whatever x is. And so we have, it's the opposite of whatever x is, which means it's the opposite of -3, which is, in the end, it's going to be +3 here. Okay, that's exactly what's happening right up here. I'm going to erase this stuff here. And so that's exactly what's happening here. This ends up being negative. And so since it's negative, the absolute value of this is going to be the opposite of what that value is inside the absolute value symbols. So now I just do, I distribute that negative. Negative times pi is -pi. Okay. That is kind of like negative pi. And then negative times negative positive, so +4, and then there's a +1. And 4 plus 1 is 5. So the answer to this is the opposite of pi plus 5. And there, I'll box that right there. So that's the answer to that one right there. Okay, the next one. We have the absolute value of this, given that x is greater than or equal to 5. Okay, so if the smallest value that this can be is 5, then when we have 5 minus 5, that's going to be 0. Okay, and then 5 is bigger from there. If we go with 6 minus 5, of course it could be decimals and such, but I'm just going with whole numbers right now. That is going to be, well, first off, 6 minus 5 is greater than 0. And so what that means is, if we go back up to this other part right up here, that means that when x is greater than 0, so this part is greater than 0, that means it's just x. So what this is just, that's the same thing as 6 minus 5. And so what we're really talking about here is that if I were to erase this, what is the answer in every case? Overall, what's the answer here? It's really just whatever x minus 5 is. Okay, and then what we have is the last case here, where if t is less than 5, let's give an example. If t is less than 5, so 4 is less than 5. So if I have 4 minus 5, that is negative. So this is negative. And when it's negative, we come back to this idea here. So when that x is smaller than 0, this is going to be the opposite of whatever x is. So this ends up being the opposite of whatever 4 minus 5 is, which is the opposite of -1, which is just 1. And that's just one example, but what we're trying to do is solve this for all examples here. I was just trying to give you an example of what's going on here. And what we can do now is we can say, I'll further erase all this stuff. So what's going to happen here is t minus 5, this part, what is it? It's always negative. It's always negative. So since it's always negative, that means it's going to be the opposite of whatever t minus 5 is. And again, if we distribute that negative to each of these, we got the opposite of t, or negative t, and then negative times negative is positive 5, and that ends up being what this is. So and again, remember, we're just asked to rewrite the expression, and that's what we did. We rewrote each expression there. And by the way, one last thing I want to say here is in our solutions here, they have they express this as 5 minus t, and that's the same thing as negative t plus 5. And so we will continue on with simplifying an expression containing absolute values. And so we see here, if we simplify the expression absolute value of x minus 1 plus the absolute value of x minus 2, given that x is in the open interval 1 comma 2. So we're not including 1 and we're not including 2, but those are the boundaries. Since x is greater than 1, the quantity x minus 1 is positive. And consequently, right here, and this goes right from our description that happens above. In fact, I'm going to copy it right here. So this little statement right here is going to get used over and over and over. And it is especially being used right here. So since this is always going to be positive, because again, it doesn't include 1, it's always just a tiny bit bigger than 1. So that means this is going to be positive, which means this is in play right here. Since this is going to be positive, the absolute value of x is going to be x right there. The absolute value of x is going to be x right there. It's going to be in play. And then what we have also is we have the second statement. And this one, so this is always going to be negative because the boundary is 2 right here. It doesn't even hit 2. So this is just like this is always going to be positive. This one's always going to be negative. And since it's going to be negative, then this is in play right here. So since this is less than 0, it's going to be negative. It ends up being the opposite of whatever that statement inside the absolute value is going to be. So we have this. This is the negative version or the opposite of whatever was inside the absolute value right there. And if we distribute, the negative times x is negative x. Also, when I say the opposite and negative, they're really meaning the same thing. And negative times negative is positive. So this statement is equal to that statement. And so we put these two things together. This right here is here. This is our original statement. And so this is equal to that, as shown up here. And this is equal to that right there. So there is that statement. And we put them together. X plus a negative x, well, they just cancel out. They're nothing. And then negative 1 plus 2 is right here. Negative 1 plus 2 is 1. So we put all this stuff together. And what I want to do for a moment is I'd love to show you, I like to use Desmos here as a graphing calculator. And what I did is I entered the 3 different expressions that we got. And I'm going to go one by one here. First off, we have the absolute value of x minus 1. So this right here produces this V-shaped graph. And I won't really go into so much why it does that. It's a little bit outside this lecture as to why it makes that. Hopefully you've seen this graph before if you're into this lecture. But we have this V shape here, and it creates what that point is 1, 0. So that's at 1 when x is 1, y is 0. Okay, and then we have this other one here, which we have, yes, there is x minus 2. Okay, but the expression that we are working on is this here. And this is kind of cool. Take a look at this. So the sum of both of these, if the sum of both expressions put together is the green graph. And it should make sense here because the sum of this is 0. And the blue right here is 1. So 0 plus 1 is 1. And then this is, both of them are 0.5 right here. So 0.5 for the blue and 0.5 for the red, makes one whole. And then as this is increasing, this is decreasing. So as I add both of these up, in fact, I think I'll bring it in tighter here. So this is very interesting. As this is 0 and this is climbing, this is 1 and it's decreasing. So the sum of both of these at each vertical point here, up and down, is consistently 1. So from 1 to 2, the output is exactly 1. And isn't that what we were talking about algebraically? If I move this aside here, that as we're talking about, continue to move it there, as we're talking about from 1 to 2 right there, the output is exactly 1. Isn't that kind of cool? I just love that stuff. Okay, so in this box it follows is really all of those properties put together. And then we got a little extra too. So for all real numbers, we have the absolute value of x is always greater than or equal to 0. Okay, can't have a negative distance. And x is less than or equal to the absolute value of x. So it could be equal to or it's less than. And this right here too. This could be equal to, because I guess it could be 0 in case it would be equal, but this will always be smaller than this. And okay, so this is nice to know too. So absolute value of x squared, same thing as x squared. Okay, so we can just drop the absolute value when we're squaring something. And then we have some other basic properties here. And this one's huge right here. The triangle inequality, that'll be the end of the exercises really focus heavily on this right here. And it culminates in a proof, which is kind of exciting. We could start our little works with proof. So right here, and for a proof, the triangle inequality, see exercise 67, which is the last one in this section. Kind of fun. And so in this, we are rewriting an expression to eliminate the absolute value. And so we have this here. Write this expression right here in equivalent form that does not contain absolute values. Okay, so x squared is not negative for any real number x. And let's get into this, because this seems to come from nowhere, right? And then they lead off, and then they head into something that we see right there. But what's going on here? Why are they saying, what's the big deal that this is positive? Well, first off, if you square x, it's never going to be negative, no matter what the number is. So you can put a number here. It doesn't matter if it's positive or negative. When you square it, because a negative times a negative is a positive, and a positive times a positive is a positive, this is always going to be non-negative or positive. Okay, and if you have 2 plus that positive number, that's also going to be positive. Why does this matter? Because if we take 2 plus x squared, okay, and if we take the opposite of that, then that is, if I distribute the negative, that's negative 2 minus, right? If I distribute this here to both of these, that's negative 2 minus x squared. Then this is exactly that. And then you realize that, oh, okay, if I have this, if this is always positive, and if I take the opposite of this, then there we go. That's negative, right? Because if this is positive, then the opposite of positive is negative. So there you go. And if I distribute that, I have this. And then if this is here, then they just kind of say, well, this is equal to that, right? And so now they get to say, oh, this is negative because this is positive, and the opposite of that is negative. Okay. Wow. And then from here, we can just use the algebraic definition of the absolute value that we were talking about before. So you have this, that is the same thing as this, right? Yes, because this is ends up being negative. And so If that's negative, then it's the opposite of what that statement was inside, and it ends up, this is positive. Oh my God. Whoo boy. Alternatively, okay, we can factor out a -1 from these. Okay, so it's -1 times that, and we can separate these, and we can separate all this by way of what's going on here. This one right here. If you have two things that are multiplied inside the absolute value, then you can separate them, and then this a right here, that would be our -1, and then that's the other statement right there. So we could do that too right here, and that's what they did here. And then the absolute value of -1 is 1 times 2 plus x. The absolute value of 2 plus x squared right here is just 2 plus x squared. So there's that. If we think of numbers as, oops, I'm trying to make this a little bit smaller here. If we think of numbers as points on a number line, the distance between any two numbers is given by the absolute value of their difference. Easy. For instance, the distance between 5 and 7, which is 2, is given by either doing this or this. And I think that there's a little graphic over here. Yeah. So this is saying the distance between 5 and 7, the distance between 5 and 7, and the distance between 7 and 5 is the exact same distance. It's 2. Okay. So it doesn't really matter. The distance between A and B can be written as this or written as that. So we have using the absolute value to rewrite statements regarding distance. Okay, so the distance, to write this right here, the distance between 12 and -5 is 17. That's how you would write it. So it's as though you have this A minus B is said to be the distance between, okay, that says between A and B. Okay, that's that framework right there. And so we're really just rewriting these statements. So if you want to write the distance between x and 2 is 4, then you write x minus 2 in absolute value equals is 4. Or you can switch this around, right? Because that's what the statement earlier just said. And the distance between x and 2 is less than 4 is written like this, is less than 4, or you can switch them around again. And the number t is more than 5 units from the origin. Okay, there you go. It's just translations right there. And displaying intervals defined by absolute value. So in each case, the set of real numbers satisfying the given inequality is one or more intervals on the number line. Show the intervals on the number line. So this right here, you know what? There's one thing, a little trick to remember. I'll say great or and less and. So if you look at this is the absolute value of x is less than 2. So what are the numbers that will fit in there? If we have this here, then from 2 to -2, all of these numbers will fit. And so I would say parentheses and parentheses, because that's the beginning and ending points, but they don't include those points. And the ands connect. They connect each other, and the ors are disconnect. And you'll see in just a moment. So those connect to each other. And the absolute value of x is greater than great or. So you have 2 and -2. And you know what? Before I continue, this is the graph of all the values that will work in here. Like what's in here? 0. 0 is about right in the middle. So the absolute value of 0 is less than 2. 1 is right here. The absolute value of 1 is less than 2. 1.9. 1.9, absolute value of 1.9 is less than 2. So those are all, that's a graph of all the numbers that fit in there. And then if it's greater or greater, then we're talking about, I'm stuck for a moment here. Maybe it's like this. And these values, okay, and then that's supposed to be parentheses, like that. So this is the graph of those numbers here. So the ors disconnect, right? So the disconnect meaning that they go away from each other, and connect meaning they go towards each other. And so if you look at like -4, the absolute value of -4 is bigger than 2 because it's 4, and the absolute value of 4 is bigger than 2. Okay, so there you go. Now we have the other parts. So for C, we would, if we were to interpret this, I mean, what does this say? It says the distance, right? So subtraction with absolute value there is telling us the distance between some number and 3 has to be smaller than 1. Let me write that down. Okay, so I wrote that down. The distance, so to put this into a sentence, the distance between x and 3 is smaller than 1. And so that means that as we have 0 and 3 is here, the distance between that number and 3 is smaller than 1. So we're talking about 2 over here and 4 over here, and parentheses, right? Because we're not including those values, but that's the boundary. And this is that space in between. That distance has to be smaller than 1. Okay, and then let's see. Let's look at our last one here. So, oh, and by the way, also look at this: less than, less and. It's an and. It connects them. Okay, this is a greater than or great or. It's going to be disconnected. And so if we interpret this, I'll write that down. So the distance between some number and 3 has to be greater than or equal to 1. And if we graph that, so we have here's 0, here's 3, and a distance of 1 means that it could be 2 and it could be 4. And we're looking at brackets here because we are including 2. And it's going to be going that way. And so that has a distance greater than 1 from 3. And if we go this way, all these have a distance greater than or equal to 1 away from 3. And so those are the disconnected graphs for that statement. And this is a whole bunch of words of basically saying what I tried to convey to you. And now we get into our exercise set. And I'm going to choose, so a few of these are pretty simple, like the absolute value of 3. Well, that's just 3. And I encourage you, I'm not going to do all of these, and I encourage you, the viewer that's working to understand all this, do all the odd ones. I'm going to do a sprinkling of these. And for instance, if I were doing number 5, I would just think, hey, this is the absolute value of -1 plus 3, which is the absolute value of 2, and that's just 2. Number 4, I would think that this would be -6 minus the absolute value of -6, which is just 6. So this should be -12. If I have 14 right here, 27 minus 5, that would be the absolute value of 22, over 5 minus 27, the absolute value of -22. And that's just 22 divided by 22, which is 1. Phew, a lot of work for just the number 1, huh? Yeah, I won't spend too much time on that stuff. Let's get into something that might be a little bit more interesting. So let's look at number 23, and I'm going to move this over here so I give myself some room. let's see, actually I can't do all that much. So if I say that a is -2, so that's -2, and then plus b, so +3, plus the absolute value of a, which again is -2, minus b, which is 3, all divided by 2. So I would then take, well, -2 plus 3 is 1, plus the absolute value of -2 minus 3, which is the absolute value of -5, all divided by 2. And so that'd be 1 plus the absolute value of -5 is 5 over 2. And 1 plus 5 is 6 divided by 2, which is 3. Not so bad. So moving on to this next section, this is where things start to get a little interesting. Rewriting these I'm going to erase this stuff here. Rewriting expressions without the absolute value notation. So let's take a look at number 25. Number 25, I'm going to move to the side here to give myself some room to work. And for number 25, we have the square root of 2 minus 1, the absolute value of the square root of 2 minus 1 minus 1. So we have to think right now. The square root of 2 is about 1.14. So the square root of 2 is about 1.14. You can use a calculator and you can figure that out. But the big point here is that this is going to be positive. And when it's positive, the absolute value is that same expression. So that's where we say that the absolute value of this is just the square root of 2 minus 1. And then we have the minus 1 right there. And then from here, we can say -1 minus 1 is -2. So the square root of 2 minus 2 is the identical expression as our original. So we rewrote it without the absolute value symbol. Let's go to number 29. I'll erase all this stuff. And for number 29, it is the absolute value of t squared plus 1. Okay, well, this t squared is always going to be positive. As a positive number plus another plus 1, right? If I have a positive number plus 1, that's going to be positive. So this whole thing then is positive, and you take the square root of a positive number as it's itself. So this is just t squared plus 1. Okay, moving on to maybe number 31. The absolute value of the opposite of the square root of 3 minus 4. Well, this is just a negative number, right? This is a negative number minus a number. That's the whole thing's just going to be negative. So when it's negative, we say that the answer is going to be the opposite of whatever this whole thing is, the negative square root of 3 minus 4, right there. So if we distribute that negative to both of these, that would be the square root of 3 plus 4. And that is that's exactly what that is. Now, usually when we look at the even numbered questions, they're often more challenging. And that's because the odd numbered answers are, I believe, they're in the back of the book. So the even ones are not. And let's say here, I, by the way, have all the solutions. So I make sure I check my stuff. And so for number 26, we have the absolute value of 1 minus the square root of 2. Oh, how interesting. Square root of 2, absolute value plus 1. And I say this is so interesting because take a look at this. Here we have the square root of 2 minus 1. And here we have 1 minus the square root of 2. So the numbers have been switched here. And what we should have is that's the same. It's the same number, right? When you take the absolute value of it, they end up being the same, exactly the same number. but we'll end up with a different result because 1 minus the square root of 2, while the absolute value is the same, we're not trying to actually find the value itself. Oh, and then this was minus 1, and that's plus 1. But anyway, this is going to be negative, right? Because the square root of 2 is bigger than 1. And 1, a small number minus a larger number yields a negative number. So this is negative. So what that means then is the answer is going to be the opposite of that whole expression that's inside the absolute value symbol. So it's 1 minus the square root of 2. And then there's plus 1 at the end of that. And if we distribute the negative to both of these, that'd be negative 1 and then plus, because negative times negative is positive, square root of 2 plus 1. And oh, look at this. These cancel out to 0. Okay, so it's really just, the answer is just the square root of 2. And these have been manufactured, right? So they just work out nicely like that. And let's take a look at number 32 maybe. 32 sounds like it'll be the most of the interesting questions. So for number 32, we have the absolute value of the opposite of the square root of 3 minus the square root of 5. So this is going to be pretty negative because that's a negative number minus more. The whole thing's going to be negative. So what that means is the answer is the opposite of that entire expression. Minus square root of 5. Okay. It was sloppily written, but hopefully you get the idea. And then, so that's negative times negative is positive, negative times negative is positive. So that is the square root of 3 plus the square, no, I'm not going to do that, plus the square root of 5. And that is our expression there. Okay, not bad. Let's look at number 34. And I think that what I'm going to do is I'm going to chop this up and bring this over here so I have a little bit more room to think. And if x is greater than 4, strictly greater than 4, so I'll just call it 5, right? So, or maybe I don't have to do so. If it's greater than 4, then this is going to be positive, and this is also going to be positive. So this is positive, and this is also positive, right? Because this would be like 5. So think of some number bigger than 4 as 5. 5 minus 3, that's positive. 5 minus 4 is positive. So so essentially what this is going to do is this is going to say, since they're both positive, it's going to be themselves. So this is going to be x minus 3 plus x minus 4. And the x's combined to get you 2 x's, and negative 3 minus 4 is negative 7. So we should get 2x minus 7. Okay, so that works out. And then let's go with another. Maybe 38 might be the most challenging of these. So I'll bring that over here, and let me erase this stuff and clean it up a little bit. Okay, so if x is smaller than negative 3, then something smaller than negative 3 is negative 4. I know that there's a bunch of decimals in between, but I'll just, if I imagine that I have something smaller than negative 3 is negative 4, then negative 4 plus 1, that's negative. I'll just write a little note. So this is negative. So that means it'll be the opposite of that statement. And then plus 4. And then if this is smaller, this is smaller like negative 4, negative 4 plus 3, that's going to be negative also. So this is negative. And so that means it's going to be the opposite. So it's going to be times. the opposite of x plus 3. Okay, so what we then have is, I'll clean it up a little bit. I would say that if I distribute the negative here, I have negative x minus 1. And then if I multiply these two together, so that'd be plus 4 times negative x. It would be negative plus 4 times the negative, I guess. Essentially, that we're looking at, that'd be minus 4 times the x plus 3. And I would then distribute the negative 4 times x is negative 4x, and the negative 4 times 3 is negative 12, negative x minus 1. These put together is negative 5x, and these put together is negative 13. And so we have negative 5x minus 13. Nice. Okay. Let's see what else we got here. All these statements are, you're really just translating it into an absolute value expression, or inequality, I should say. So maybe 47. I'll jump down to something like number 47 is what the distance between. So the distance between boom, boom, boom. That's the distance. That's the framework for distance between, or template or whatever. And then x squared and a squared, okay, is less than m, less than m. And now this one is a very nice one, number 48. Let me give my scooch over and give myself a little bit of room for this. And let's translate this exactly. Sum of the distances from A and B from the origin. Okay, the sum of the distances of A and B from the origin. So the distance between A and the origin, boom, and the origin is 0, right? And the sum of those distances. So that's one distance, and then the distance between B and 0, okay, or B in the origin, is greater than or equal to the distance of A plus B from the origin. So the distance between A plus B from the origin. So that distance to the origin. Okay. Now we can take out the minus zeros in all this case, because I did this word for word explicitly. But if we take out the minus zeros, you're really looking at the absolute value of A plus the absolute value of B is greater than or equal to the absolute value of A plus B. Well, that is the triangle inequality theorem. So that's valuable. That'll lead us into exercise number 67 for sure. And that leads us into these graphs for these. So maybe for 49, do a few of these. Number 49, this is a less and, right? Less and, these are going to connect. So the absolute value of some number needs to be smaller than 4. Well, that means we have between 4 and negative 4, and it's parentheses. It's not including those points. It's all of those points in between 4 and negative 4 are going to work in there. We can go to number 54. I think gets a little bit more interesting. So if we look to, if I start this here, and I have to, now I want to directly translate this. The distance between some number and 4 is smaller than 4. So if I look at some number in 4, maybe what I want to do is expand this a little bit further. And I'll go farther like this. Maybe I'll have 0. Okay. 4 is over here. So the distance between a number and 4 is smaller than 4. Well, that means that that distance is smaller than 4, less than 4. So this has a distance of 4, and if I go out to 8, so if that's, the center point, That has a distance of 4 also. So, and then we're looking at not including those endpoints, so those parentheses come out here. And there you go. That's it. Uh, Taken directly from translating this, then all of these have a distance of less than 4 away from the point 4. Let's look at, that one won't be as interesting. Maybe 58 and 60. Let me erase this stuff here. So 58. Now in 58, we're no longer talking about the difference between these two. We're talking about the sum of them, so the sum of the distance between the sum of these and the distance to 0 is, oh yeah, that's how we can do it. That's how we can look at this. So on number 58, trying to think of an intuitive way of doing this, x plus pi over 2 minus 0 has to be greater than 1. Now, I've been round and round thinking about how to intuitively explain this. My easiest explanation is this. Let's remove that 0. So let's rewrite this. Absolute value of x plus pi over 2 is greater than 1. And what we usually do, if you've been through Algebra 1 class or Algebra 2 class, we usually split this into two different statements. X plus pi over 2 is greater than 1, the original statement, and then we will negate all of this, where you have, not all of it, so we have x plus pi over 2 less than negative 1. See, so this part right here has been switched over. This will give us our entire range of possibilities. So if I subtract pi over 2, subtract pi over 2, and x is greater than negative pi over 2 plus 1. And I guess I didn't need the absolute value symbols there, but if I subtract, so I'll just erase that little part right there. And minus pi over 2 minus pi over 2. We have x is less than negative pi over 2 minus 1. And now if we work to graph this, to graph it, then we have x is, so the opposite of pi over 2 plus 1 and the opposite of pi over 2 minus 1, and we have those two, so x would be greater than, so parentheses going this way, and x is less than, and parentheses and going that way, and that would be our graph for that. Let's go on to our later problems here. This is where things get pretty exciting. Let's talk about 62. So show that for all real numbers a and b, we have the absolute value of a minus the absolute value of b is less than or equal to the absolute value of a minus b, beginning with the identity. This. Okay, wonderful. Take the absolute value of each side and then use the triangle inequality. I'll write this stuff down on the side. And so we're going to start with that hint that they give us. So since a is equal to a minus b, but then if you add b, okay, b's would cancel out, then we would then say the absolute value of a is equal to the absolute value of a minus b, parentheses, plus b in parentheses. But then we could use an earlier property that I'll pull that up from earlier in the lecture. Okay, so I dug that up, and it's right up here. And I'm going to use this one right here. A plus absolute value of a plus b is less than or equal to absolute of a plus the absolute value of b. And I'm going to apply that to this. So this is then, you know what, I better kind of move. I can't move it, but I'll just squeeze that in there. So that means this has to be less than or equal to. Ooh, that's a big dot. Oh well, okay. That has to be less than or equal to the absolute value of a minus b plus the absolute value of b. So what I did is I took this. This is this right here. Boom. And then this b is the b, which is right there. And that's supposed to be just a regular b right there. Okay, so now what we can do is we can kind of take that statement again and rewrite this. So this a right here, absolute value of a is less than or equal to, and I'm just going to leave that, I'm going to leave this middle statement out, and I'm going to jump right to here, and write that down. So this is less than or equal to the absolute value of a minus b plus the absolute value of b. And then what I could do is I could subtract the absolute value of b from both sides minus the absolute value of b. And so what I have left here is the absolute value of a minus the absolute value of b is less than or equal to the absolute value of a minus b. See, this just got written right down there, and then these cancel each other out, so that's fine. That's what we were trying to move it over here. So absolute value of a minus the absolute value of b right here, and there you go. There's the statement that we're trying to prove right there. So there it is. Number 64, I think this might be an easy one to kind of pick apart here. Why are there no real numbers that satisfy this equation? Well, first off, how can you take the absolute value of something and have it be negative? Absolute value is, mostly about distance. How could this distance to 0 be negative? You can't have that. And so since it can, if we, the best we can do is we could have the absolute value of x squared plus 4x is greater than or equal to 0. That's as low as we can go. We can go or equal to 0. I could say equal to 0. That distance could be equal to 0, but it can't go below 0. That distances can't be that. Okay, now we're to the bread and butter here. Let's consider number 65. Let's do 65, 66, 67. So 65. As a background for this exercise, you might want to work number 23. Okay. Well, looking back, number 23, we have, it's one of those substitute ones. Did I do that? 23? Oh, I don't know. I don't remember doing that one. But let's assume that I did. Okay, so let's go back here. Okay, let's prove that the max of a comma b, so the maximum of a and b is equal to exactly this. And so what we have is we would have 3 cases for this, because we have case 1, where a is, well, if a and b are the same, is if a is equal to b. So what would that be? That would be a plus b. So a plus b plus the absolute value of a minus b, all divided by 2. So a and b are the same. So I could have everything being a, really, just everything's just in terms of a, because a and b are the same. So there'd be a plus the absolute value of a minus a, all over 2. So a plus a is 2a, and then the absolute value of a minus a is 0, so plus the absolute value of 0, all over 2. So that would be 2a plus the absolute value of 0, 0, all divided by 2. So this is really just the absolute value. It's just a, the value of a. Okay, so that's if A is equal to B. Case 2 is where A is greater than B. And so when we have A plus B plus the absolute value of A minus B all over 2, what do we have? Well, a little bit of trickery here. If A is greater than B, if A is greater than B, and if I subtract B from both sides, then A minus B must be greater than 0. And that's key. Because if we have it greater than 0, then first off, A plus B, okay, A plus B. And then if this is greater than 0, then that means this is exactly its same statement. So that would be plus A plus B, oh, plus A minus B all over 2. And what we have is we have two A's, and then the B's, B minus B, just cancel each other out over 2. And so once again, we have A for the value. Okay, and then the last case is A, case 3. A has to be less than B. Okay, so that means that if I subtract B, once again, A minus B is less than 0. And that is key right there. So we would have in our A plus B plus the absolute value of A minus B, okay, over 2. Then what we have here is we have A plus B and then plus the, so since this is going to be, since this is less than 0, this is going to be the opposite of all this. So plus the opposite of A minus B, okay, all over 2. Let's move this up just a little bit. So we have then A minus A, right? We have A minus A. Maybe I'll just clean up the whole thing. A plus B minus A. So if I distribute that, minus A, and then that plus B over 2, then the A's would cancel out, and the B's would, there'd be 2 B's over 2, and the 2's cancel, so that's just B. Okay, so there's that whole thing. And 66 would work in a similar fashion than 65. And then finally, we get to go to the eventuality of this entire lesson is number 67, proving the triangle inequality theorem. And I have a couple of ideas on this. This I might spend a little bit of time on. Let me erase all this stuff here so I can give myself some space. And, you know, when I think about the triangle inequality theorem, I think about, well, first off, what is the triangle inequality theorem? It is this. It is that. The triangle inequality. Yeah, triangle inequality. And why? I mean, you got to wonder, first off, in this theorem, which they don't even call it a theorem, they just call it, it's just a triangle inequality. It's just a statement. But where's the triangle in this? Right? Where is the triangle? There's no triangle here. But I've taught for a long time, and in the geometry unit, we have to talk about that. So we would have like this. We have triangles, okay? And this is where it comes from. If this is A and this is B and this is C, then A plus B has to be greater than C for this to be a triangle. So the sum of the two shorter lengths, the sum of these two lengths has to be longer than the third length. And we can see here that that's really where this is coming at, right? The absolute value of a, so a, right? So that length plus the other length right here, these two lengths have to be longer than the sum. So these two lengths have to be longer than c. So this would be our c. This would be the, it has to be longer than the sum of those two in order for this to produce a triangle. That's why it's called triangle inequality theorem. And so now we can use, I don't know, this as the backdrop of our proof for this. So let's go with A. So what's really nice about this is, first off, students, if you are considering math as a major or something you might want to study later on, you've got to be good at proving things. And this is exciting. Precalculus, you won't really have to prove stuff until after you finish the entire calculus series in probably linear algebra, and then you got to start proving stuff. So it's nice to take baby steps right now, and that's exactly what this is doing. It's giving you some baby steps along the way. So let A and B, let A and B be real numbers. Which property in the summary box on page 7 tells us that A is less than the absolute value of A and B is less than the absolute value of B? Well, I grabbed that from page 7 right here, and so what that does, which one is it? It is this one right here. A is less than the absolute of A. It's right here. It's B. Property 1, part B. Okay, so maybe 1B, something like that. I add the two inequalities in part A to obtain that. Okay, I'll do that. I'll move this stuff aside and do that. Okay, so I have A plus B is less than or equal to the absolute value of A plus the absolute value of B. Okay, nice. In a similar fashion, add the two inequalities of oh, whoops, I forget to do this right here. Okay, and deduce that. Okay. So in that fashion, I will put C here, and since the opposite of A plus the opposite of B is less than or equal to the absolute value of A plus the absolute value of B. Yes, we've had these statements, and that goes along with what had just been said about this right here. We're taking each piece of it. So that and that. Okay. And so as we have that, that means that so I will put a comma here, and so we know then that the opposite, putting these together, the opposite of A plus B, okay, is less than or equal to the absolute value of A plus the absolute value of B. Just doing a little bit of a reverse, factoring out a negative, you might call it, reverse distribution. And then for D, why do the results in B and C imply that we have that triangle inequality theorem? So, okay, let me erase this a little bit here. Give myself a little bit of room. And we would say that since this we have A plus B is less than or equal to, less than or equal to the absolute value of A plus the absolute value of B, okay, our statement, and we know that the opposite of A plus B is less than or equal to the absolute value of A plus the absolute value of B, including the other statement we have, the absolute value of A plus B is less than or equal to the absolute value of A plus the absolute value of B. Okay. Then the absolute value of A plus B is either either just a plus b, or it could be the opposite of a plus b. Either way, you're getting the positive version or the negative version. It's just the absolute value of that whole thing, which is exactly what this is here. Spend a little bit of time soaking this in. These are the baby steps to proving ideas and theorems. It's an exciting little step on your journey towards calculus and beyond. Well, I hope that you've enjoyed this lecture. I've had a fun time putting it all together, and let me know what other exercises you tried or any questions you have. All right, till next time. Bye.